All right. Well, welcome everybody. Welcome to the Scott Institute for Energy Innovation here at Carnegie Mellon. My name is Daniel Tatching. I'm the executive director here at the Scott Institute, and we are so excited to have you here today to hear from our distinguished speaker today. And because today's distinguished speaker is going to be talking about two extremely important topics, energy, which is represented by the Scott Institute, and security, which is represented by the SciLab Security and Privacy Institute here at CMU. We have two of the biggest institutes here on campus focusing on energy and security, co-hosting and co-sponsoring today's talk. So a big thanks to SciLab for the support of this great event. If you're unfamiliar with the Scott Institute, we are CMU's hub for all things energy and energy research and entrepreneurship. We have over 170 different faculty from all across campus in our School for Economics, our Computer Science School, Engineering, Social and Decision Sciences. As you all know in the audience, energy touches so many different areas, and because interdisciplinary work is in our DNA, it is the Scott Institute's role to make sure that all of those folks are working together. So we give out seed funding each year to grow new innovative research projects. We also support new energy research initiatives, again, across campus initiatives. This is more than just supporting a single faculty on a project. We do that too, but we also are very deliberate about making sure we're forming strategic teams across campus. We also help create and grow we host a variety of different energy and climate themed events, such as today's distinguished lecture, and we also support our energy startups and entrepreneurs on campus. If you want to keep in touch, we are on LinkedIn, we are on X, and we're on the web. But probably the best way of all of them to keep in touch and to learn about all the activities that we have going on at CMU around energy and energy, climate, research and entrepreneurship is to join our newsletter. So as you were checking in at walking in the door, we had a QR code to join our newsletter. You can also pull out your phone and scan that. This is the best way to keep in touch of what is going on at the university in in energy research and entrepreneurship. We only email you once a month. We don't spam you. We know emails are crazy, so please sign up to stay in touch with what's going on. So before we hear from today's distinguished speaker, I would love to invite Kostas Samaras, director of the Scott Institute and a professor of civil and environmental engineering, to the podium to share a few remarks and to introduce today's speaker. So Costa, the stage is yours.
Well, welcome everyone. I'll be brief. I really wanted to first thank you for joining us for our first distinguished lecture here of the fall, and really to celebrate what Daniel mentioned is the mission of the Scott Institute, which is to enable a secure and resilient net zero future for everybody. And part of that mission is to do deep interdisciplinary research, and that is the topic of today's distinguished lecture. We are so grateful to have our speaker today, Juan Torres, from the National Renewable Energy Laboratory. Juan serves as the Associate Laboratory Director for Energy Security, Resilience, and Integration, and he oversees NREL's research on power systems engineering, energy security, cybersecurity, and energy systems resilience, all topics that we do very well here at Carnegie Mellon. NREL's work supports the goals of delivering integrated solutions to ensure the energy systems of today and tomorrow are reliable, resilient, and secure. Torres co-leads the lab's research strategy for the Advanced Research on Integrated Energy Systems platform, the nation's most advanced platform for energy systems integration, research, and validation, which can replicate any energy system and grid scenario at real-world scale, risk, and impact. From 2017 to 2024, he served as a co-chair for the U.S. Department of Energy's Grid Modernization Laboratory Consortium, a partnership of 14 national laboratories to advance modernization of the U.S. power grid. Prior to joining NREL in 2017, Torres served in a variety of technical and management positions throughout his 27-year career at Sandia National Laboratories, most recently as deputy to Sandia's Vice President for Energy and Climate Programs. Please join me in welcoming today's speaker, Juan Torres.
Thank you. Everybody hear me okay?
Great. Okay. Clicker.
Awesome.
Down advances.
Perfect. And I'm going to walk around a bit. I don't know if it's going to drive your camera crazy, so you're good? Okay. Let's see. Down. Yeah. The other down. Okay, all right. Kind of troubling to see my picture that big on the screen too. So thank you for joining us today, and thank you to CMU, Casa Daniel, for the privilege to speak in front of this audience. My first visit here to CMU, but I collaborated with CMU over the years, with research in my career. Let me give you a little bit of background about my journey, because I think it's really important to understand my perspective and our perspective there at the laboratory. Why I'm there actually is not something by happenstance, why I'm at the laboratory and why we're working specifically in energy security at NREL. I'm going to start out with, well, it's my picture again, unfortunately. Focus on the pictures on the far left here. These are my wife and I have had Scotties now. Those are the only kinds of dogs pretty much we've had over the year. And I had this discussion earlier at SciLab. Are there really white Scotties? Yes, these two are actually related. So I have a white Scottie and a black Scottie. These are our second set. And so I did not realize that your mascot here was Scotty until about a week ago. My daughter told me. She's like, "What do you mean you didn't know that?" So a little bit more about my journey and where I see energy and energy security. It's important to understand where we came from first. In my career at Sandia National Laboratories, those of you who are not familiar with Sandia, it is one of the weapons laboratories. Nuclear weapons tied to the Manhattan Project. If you saw Oppenheimer, Sandia was responsible for all the engineering that went into the design of the first weapon, and that is still their core mission. My work there early on was supporting defense in protecting the U.S. from a incoming attack, a nuclear attack. Sounds pretty daunting and kind of scary. And I thought I'd never even have to think about that again in my career after I moved, which is unfortunately we're in a really interesting place in history. But early on in my career, I focused heavily on networks and design of systems and platforms used by the military before cybersecurity was a word. And in 1998, I was asked to do an assignment in Washington as part of what was the Critical Infrastructure Protection Task Force in response to President Clinton and a committee that was formed, President's Commission on Critical Infrastructure Protection, that identified at that time 6 critical infrastructures. And we were just trying to figure out what are they. We didn't have a full understanding of the threats. And I was doing some research in the early days around the power grid. One of my tasks was to identify, so what threats are we dealing with? This is 1998 or so, 1999. All I could find documented, there were no attacks on the U.S. power grid with the exception of bored hunters that were shooting insulators because they didn't find anything else to shoot. Or down in South America, there was a tribe down there that didn't want transmission lines going through their part of the jungle, and they were knocking over transmission. So that's what we were dealing with back then. The way our infrastructure evolved over time, essentially, we felt the U.S., I mean, we're essentially exposing all of our organs by building things out in the open. Transmission lines, power lines, communications lines, they're fully exposed because we always assumed the threat was coming from outside. So we protected the perimeter with our military and assumed everything internally was okay. We could trust everybody internally. And we saw during 9/11 that wasn't necessarily the case. And with the advancements in digital technology, incorporation of digital technology in anything and everything in our infrastructure, that also opened those systems to the threats that we're seeing across the board in cyberspace. So that's kind of painted the history of where I've seen it. I've been involved kind of from the beginning to where we are today. And in 2017, Lab Director Martin Keller at NREL, who's Lab Director then, asked me to come because we saw a huge need as the renewables penetration was increasing, not just within the U.S., but globally. And we needed to understand where are the threats going to those kinds of systems. So that's my my story to where we to how I ended up at NREL. Those of you not familiar with the national laboratories, there are 17 Department of Energy national labs. There are also some DoD laboratories as well. Focused on these 17, there are a lot. Most of them have their history tied back to the Manhattan Project, with the exception of a couple. We are one of those. So you'll see us in the middle of the country there. NREL is located in Golden, Colorado. We also have a campus out in Alaska. We'll talk to those in a second. And then we work closely with the 3 weapons labs, Sandia, Los Alamos, and Livermore National Lab. And then there are on the order of 10 Office of Science laboratories that you may have heard of. I understand Brookhaven is here recently. There are also other laboratories like Oak Ridge, Pacific Northwest National Lab, Lawrence Berkeley Lab. So we are part of a bigger ecosystem. We are one of 3 applied laboratories, applied energy laboratories, I should say. They're Idaho National Lab. They are actually a nuclear energy laboratory as one of their primary missions. And of course, they do a lot in national security and cyber. The National Energy Technology Lab, which is located here. You should know them pretty well, right? Here and in Morgantown, in Pittsburgh and Morgantown, and then NREL. We have what we call more the Energy Systems Lab. We're not just renewables anymore. As a laboratory, we're a little over 4,000 people or so. We've grown very quickly. We're the most outward-facing laboratory because our mission and our entire mission is energy, and the vast majority of the energy infrastructure in the U.S. is not owned by the U.S. government. There's bits and pieces, but largely we work with utilities, the vendors, and all the various stakeholders. So we're a fairly large lab. We have a lot of partnerships per capita, more than any other national laboratory because of our mission space. So we do a lot of work with academia, with industry and other parts of the government, as well as with other nation states. So we are a big player globally as well. All right, so as a laboratory, these are the kind of the 4 areas of science that we work in. We have more recently branded ourselves as what we think is more true to who we are. We are an energy systems laboratory. So we work on everything from the materials, to the devices, to the systems, to the markets, to the policies, to understanding regulations, standards. So every aspect of energy systems, from how you capture and transform and make it into some sort of a usable form, to how you move it and store it, to how you use it. Right. So the entirety of the energy system, and of course security being a big part of that. So I work in that world mostly. Also heavily working in transportation and fuels. That's where that's an element of the energy system itself that's changing energy as a whole. Buildings and industry, from materials to energy efficiency and how we use it in buildings, homes, communities, and so on. And then, of course, our legacy around how you advance solar cells, how you integrate those into systems, how also capture of wind energy, water energy, marine hydrokinetics, hydrogen, and just about anything and everything that works in the generation space. These are photos of our different campus sites. Our main campus is what we call South Table Mountain campus in Golden, Colorado. If you've never been there, we actually have 2 campuses. The second one is the Flatirons campus. It's where our large-scale experimentation takes place. We have a small campus in Alaska at the University of Alaska in Fairbanks, and then we have, of course, folks in Washington all the time. So it's a little bit of the background. All right, let's get into the meat of the talk here, which is around energy and energy security. I'm going to talk about these different areas that we believe are important areas that we need to pay attention to. They're not necessarily comprehensive. There are a lot of other things that we're working in, but in the energy security space, at least we'll talk a little bit about these items. One is around autonomous systems. We talked earlier, we talked about the use of AI concepts, technology, and application to pretty much all aspects of energy for planning purposes. And, you need data. Can you make synthetic data? Can you be can you actually do permitting faster? Can you use AI to help you with that? So a lot of other things we can do in planning energy systems. In understanding where cyber comes into play in the energy system. The history I talked about briefly also kind of follows and tracks the evolution of technology. Early days in technology, digital technology, I should say, it started with analog technology going into, say, the grid. Analog sensors to be able to understand the state of grid, so you don't have, something breaks, you don't have to deploy a team of people to go out there, linemen to go out there and look at things. You can see immediately there's something wrong. Is it a frequency issue? Is it a voltage issue? Did we just lose the line entirely? That's advanced now with a ton more digital technology, and we've progressed to the point that we use pretty much things that you see in IT are used on the business side of these systems. But the OT side, the operational technology, is also moving very, very rapidly. So a big challenge there is how can we make the systems of tomorrow much more robust, but also taking into account that we have to live with legacy technologies that are in place. Typically, investments in the energy sector could be for 20 or 30 years. So, and we know that the threat moves much more quickly than that. Data centers are the big word right now, and artificial intelligence. This is where a lot of this is going to happen at these large data centers, and these are huge impacts for energy use. Also, tons of benefits, of course, with what we can do with AI. But this is really shaping where energy is going right now. Supply chain, huge challenges there. Because we are now they're global markets, and where we get not only hardware but also software and firmware. And a concept to be a little provocative here is to think about how a strong energy system could be a deterrent, actually, for adversaries. So we're going to touch on each of these. In the autonomous system space, this is in an application to energy systems specifically, and we're working heavily in this particular space. The number of sensors that are being deployed, the amount of information that's coming in to owners, to operators, and even to us. I don't know if everybody here has a phone. Everybody here have a cell phone. All right. I can't live without my cell phone, it seems, anymore. And I use it for everything, including I can control my HVAC, my thermostats, I can program things. And so we are now to the point there where not only on the generation side, but on the end use side, AI and autonomous systems are going to play a huge role in this space. So we want to make sure that as these technologies evolve, that we have a good understanding of the implications of adding this autonomy. Lots of benefits to these things with the amount of information. Operators at utility control center, they need support, they need help. The system is now has so much data, and we need to make decisions much more quickly based on that. On more data. How can we do that without adding some additional autonomy to the system where maybe human intervention isn't needed? Maybe we can actually make the system smart enough so it can make certain decisions without humans in it. So there's some things to think about there. Intrinsic cyber design, and what we want to get to, and we talk about inherent cybersecurity. What does that really mean when we don't understand what the threat will be in 10 years, let alone in a year? Where we're seeing AI evolve right now is it could be a great tool to help us secure systems, but it also can be a tool against our systems. So what can we do to increase trust within these systems? What can we do to better understand what these systems mean to the evolution of cyber threats, cyber resilience? I talked a little bit about data centers, and here we really need to understand what is a data center, what more is there inside this. We've got some activities in an initiative called Chip to Grid, where we're trying to understand all the way from, well, I usually look at, I describe this as, when we're talking about AI and data centers, energy for data centers and energy for AI, but also AI for energy. How can we use these tools to actually help us manage and operate the energy system itself? And what we're seeing with data centers right now, there's a lot of talk around putting in big data centers to really help the U.S. Be a leader in the AI space. These are massive energy consumers. We're talking now gigawatts of power potentially required by a single system, and these systems operate differently than most loads. Or I should say, than our typical building loads. When we're in a building like this, the utilities, they can typically plan in advance what the loads look like. We have ways to plan out how much generation we're going to need based on things like weather. They take into account things like weather, time of year. We anticipate hot days. We can plan for a lot of people bringing on their AC. Very cold days, people are running their heat, things like that. Data centers, the dynamics of the load swings on those are very, very rapid. They can climb and drop within a second, large amounts of load. And so just adding big generation, which most generation, the large scale generation use the thermoelectric plants. If you're talking about a coal plant or a gas plant or a nuclear plant, or even when you're talking about turbine-based plant like a hydro dam, they are electromechanical systems. You literally have a physical turbine that's spinning. You're spinning a big magnet. Mechanical systems have inertia. You can't slow that thing and change the speed very quickly. So this is where power electronic devices come into play. Well, power electronics imply digital technology, right? So it's really important to understand where this is driving not just the amount of energy generation needed, but how it operates. So this is fundamentally going to affect how we're operating the grid. Supply chains, I mentioned this earlier, and this is something that over time has really affected us, and we hadn't really thought about it. In offshoring some of the manufacturing for various technologies and going to manufacturer sources because of the price, because things are cheaper, I think in the short term may have been a big win. With regards to security, it's a huge challenge. So now we're procuring not just electronics, not just hardware, but software and firmware. And over the life of a system, that firmware could be updated and modified over time. And can you track where it was modified? Can you track where it came from and who's touched it over time? So how do you manage that? How do you control that? How do you understand what the implications are on the supply chain from all these different changes, these different technologies? And the number of providers, the number of technology providers, just because of the rapid innovation that occurs and all the new startups and companies that are coming into the game, that makes it even more challenging. And a thought on energy security as a deterrent. This is something we've talked about. It's almost like well, an analogy might be in nuclear weapons space. One way to deter the adversary from ever using their weapon is you show them that you have bigger, stronger weapons. So from an energy perspective, can we do things to show that our energy system is just so robust that people won't try to do anything with it? I will tell you, if you've tracked the history of attacks on our infrastructure, let's see, who remembers more recently Colonial Pipeline? You all remember that ransomware? Okay, That was a natural gas system. Who remembers the first cyber attack on a power grid that actually knocked the lights out? You remember do you remember which one it was? The one I was going to point to be the Ukraine was the largest one, 2015, 2016. That was essentially a precursor by Russians to eventually invade Ukraine. What we're seeing is that typically anytime there's sort of a nation state attack on another country, is that cyber is typically a parallel or a precursor activity. Because energy is foundational to everything. Without energy, you have no telecom. Without energy, you really don't have any transportation. Without energy, you don't have anything. So if you can control the energy system, then that really limits what a country can do in response. So how can we make that so robust so that isn't a target, or it minimizes their interest in that system? Some of the things that we're working on at the laboratory. As the Energy Systems Laboratory, we do, as an applied laboratory, we do fundamental research. We also do a lot of mostly applied research. So ultimately, getting that research deployed, working in commercialization of the technology and the concepts, working with the various partners, taking things, working with the universities so we can take things from concept to real deployment, getting things commercialized, demonstrations. So we have not only modeling laboratory capabilities, bench scale capabilities, but also large experimentation capabilities for validation. I'll talk a little bit about that. One of the concepts I've got, let's see, hang on for a second. Okay. One of the concepts, we talked about the fact that humans, especially those that may be working in a control room for the utility, for an energy system, are just being bombarded with so much information today. And it's going to increase. So how can we use artificial intelligence to support their missions, their functions, their operations? And one way is a concept we're calling the control room of the future. Here's an example. So you recall many wildfires were occurring or have been occurring, and it seems like they just continue around the country, even up into Canada, places where they typically did not have a lot of wildfires. But we're just starting to see that this is routine anymore. And somehow we have to adapt, respond, prepare for, and work through these fires. So imagine out in the California area, there's weather events that occur. That already complicates things. And then understanding what that impact might be on overall operation. In some cases, utilities may actually disconnect substations so that they don't contribute to, or maybe the winds are blowing really hard. As we saw, you all remember the Lahaina in Hawaii, the big Lahaina fire that was proposed there to be started by sparks from a utility line. So they want to minimize that. So that's a lot of information. Now, how do you take that from what's going on at the high voltage, at the bulk transmission level, understand at a local level, how does this affect local distribution? Which loads should we take off? Which should we bring on? Another situation I saw this, and personally, my family experienced it. Do you remember the Texas blackout that occurred a few years ago, right, during the cold? Both of my kids are living in Texas, so they were affected, and I was getting phone calls saying, "Dad, I don't have any heat. Dad, I can't charge my phone." Right? So what do you do there? And I told my son, well, go to your car, start it up, get warm, charge your phone, and then let's figure out where you can go stay. And it's really interesting that they were managing the blackouts at the various substations to high priority loads. And he ended up on the other side of the street where his power is being fed by a lower priority substation. And so there's decisions like that need to be made real time. Usually they have some order of prioritization, but many times real time they have to make some calls. And where they might have some other issues impacted locally by smoke and other implications, consequences of whatever event may be, whether it's a wildfire or other storm event. So it kind of paints a picture of a ton of information. If the system is stressed, can the owners or the operators of these systems make the right decisions, the best decisions? Another area we're working in is the advancement of standards. So there's, let's see, those of you that have worked with renewables, maybe you're not familiar with renewables, but historically, those technologies that are connected to the grid using inverters, inverter technology, those were designed to be what they call grid following, what's termed grid following, meaning if you have a solar PV farm or a solar PV system on your house, for example, it's designed to operate as long as it sees the grid. If the grid isn't there, the utility grid isn't there, it shuts off. And the primary reason is safety, because if they need to go check on a line, they want to make sure it's de-energized and your PV system's not putting power on the line while they have somebody working on it. That's great, but now that renewables have become such a bigger part of our energy system, they can actually be used in what's called grid forming function. And that requires some changes in the controls and some of the power electronics, but ultimately the standards, so that they know how to connect and disconnect those for safety reasons, but also they can actually add resilience to the system. They can help the grid ride through disruptions when normally, if they sensed any kind of perturbation, they would just disconnect. So this is a huge area for us right now. In fact, about $25 million worth of work going in this space, and we're leading the standards work in this space. We talked, I mentioned earlier that transportation is really changing the load side of our energy infrastructure. Charging vehicles, when you charge, where you charge, and that all the communication that has to take place to do this effectively, to track the payments, to assure that everything is operating as it's supposed to, is really important. So working standards of how you do this, working advancements in the various technologies, the charging technologies, is really important. One of the capabilities I have the privilege of co-stewarding at the laboratory is ARES, and Costa mentioned this earlier. ARES, Advanced Research on Integrated Energy Systems. The idea here is to bring together, I can't remember if I have this, okay, is to bring together capability at one of our facilities called the ESIF, Energy Systems Integration Facility, where we do research up to 2 megawatt scale in the laboratory, and we can work up to hundreds of physical devices in a laboratory. When I say physical devices, it could be, RTUs, PLCs, devices that interface or that help us control elements on the grid. We have distribution level voltage equipment. And then at the Flatirons campus, the large campus, we can go up to 20 megawatt scale. We can have thousands of physical devices. But what is really unique here as well, and we had some of this discussion earlier, I know with some of your faculty, is that this is great if you can do some validation, if you can understand what's going on at a 2 megawatt or 20 megawatt scale. But the reality is that's not how the world works. We have multi-gigawatt scale systems. We have entire regions of the grid. The Texas grid is alone, ERCOT is pretty sizable, and we've been able to emulate the entire Western grid. There are three, the three major grids: the Eastern, the Western, and then ERCOT Texas. How do you understand what the implications are of some of the things that are being proposed in energy technology changes, in cyber control changes, things like that? So ARES allows us to scale with the virtual emulation environment to millions of devices, to gigawatt scale, whatever size you want, and bring hardware in the loop so that this is not just a simulation, but emulation working at real time. So that's some of the unique activities. And a key element that we have there is our cyber range. Where we're seeing significant change around energy system is at the edge of the grid. We work at all voltages, as I mentioned earlier, but where we're seeing things change much more quickly are from the substation down to behind the meter where the consumer sits. That's where new technologies are coming in all the time. Everybody wants to connect everything to their Wi-Fi network at home, right? That's just where we are. Virtual power plants, also a big piece there. And the other big challenge is that tightening of the interconnection, the interdependency with telecommunications. So cloud technology also being used heavily in this particular space. So that's complicating things even more and more. Again, it's just starting to blur. What we're seeing, how we're managing and operating these systems is very challenging to understand where the one piece starts and another piece ends. So the cyber range allows us to take a look at some of these things. I talked earlier about, getting to intrinsic or inherent security, some of the activities we have going on. Cyber-informed engineering is an activity we have going on with the Idaho National Laboratory. And it's really starting to think about in the design phase, in the research phase, even as we're contemplating new devices, new technologies. Can you, from the very beginning, design out things you don't really need, or at least take a different approach than you might? As the typical approach to add cybersecurity is you do it after the fact. You bolt it on after. You go for performance, you go for cost, you figure out how to put things out there, and then you decide, oh, but I got to connect it to the network. Then let's secure it with the firewall. You may already have put in some vulnerabilities within the system before you ever deployed it. So can we think about that earlier in the design phase? We have some work going on in a program called CECA, Critical Energy Cybersecurity Accelerator. And the idea here is to bring owners and operators together, cohorts. It might be a set of utilities that say, we are all very, very interested in how you incorporate, let's just say, energy storage or EV charging, and we want to address cybersecurity issues. So they shape the problem area as a cohort, and then we work with vendors who are developing technologies to address some of those problems, and then we review them. We may even test or validate some of the things and provide feedback for improvements. And the idea is there to move that technology to deployment faster with the best security concepts as we can get. So working closely with the end users. Cloud Zero, looking at where cloud fits in, because cloud is everywhere in just about anything and everything we do. But within the utility space, we're seeing this is a huge part of what they're doing. How can you make sure that you have the most robust, secure use of cloud technology within energy? I talked about supply chain, and I'm going to hit it again just because it is super important. We're running into significant challenges in this space and doing work in AI. In fact, right now, using things like our scanning electron microscopes to rapidly, with AI added to it, to rapidly look at circuit boards, identify where do chips come from, what chips are on this board, and then be able to go beyond that as well to understand, okay, so what firmware might be within these devices. I think you saw this one, Daniel, when you were at our place. And so we're also trying to understand at the bigger picture level. So the utilities ask us all the time when we identify a vulnerability. Let's say there's a 0-day comes up, something I hadn't seen before. Where's it sit in priority? Like I see a ton of vulnerabilities. I see a ton of scans. There are tons of port scans happening constantly on our energy system networks. It's just routine. Where are they coming from? Is this something I should worry about? What are they looking at? What are they looking for? And it starts with understanding when they prioritize things. It starts with understanding what the potential consequences are and what would you do. And this is actually some work we're doing right now, we're demonstrating what if a cyber attack occurs while the system is stressed. And this came out, I told the story a little earlier, out of a big exercise that happens biannually, where all the major utilities and the FBI and the Department of Defense and all, the intelligence agencies and so on, they're part of something called GridX. It's a biannual exercise to just kind of run through what would we do if there were a major event, a major attack on the grid. And over the years, they progressed from a physical attack, active shooter, which, if you recall, anybody remember? Oh, you guys are too young. Anybody remember Metcalf? Does Metcalf mean anything to you all? Yeah, you can Google it. 2013, when I was talking about where threats, attacks on our energy system have evolved over time. 2013, Boston Marathon. Okay. Everybody was focused on, there was a bombing, Boston Marathon, if you recall. Everybody was focused on that. Same day, somebody took a rifle and shot out some transformers up in the PG&E, Northern California area. Really interesting. Somebody knew what they were doing, because they also went in and cut fiber optic cables. Why would they do that? If I cut the cables and I cut your eyes, your sensors essentially, you have no idea why that power just went out. So essentially a physical attack on the cyber system on that one. So couple that with, if this were to an attack like that, let's just say a cyber plus a physical attack occurred at the same time, you're dealing with a wildfire event or a hurricane event or a major cold freeze or maybe multiple. Could you tell, especially if since we know, and it's public out there, you can read about this, there is pre-positioning of software, cyber, we'll just say cyber exploits on our infrastructure. Things are already deployed in there. Maybe just waiting for something to happen when the system is stressed. Could you tell if the response of the system was due to a cyber attack? Could you tell if it was just because the grid is stressed, because you lost some sensors? Makes it hugely challenging. So we're doing work in this space to understand everything from the threat to what would happen to the energy system, to the potential cyber means, and ultimately, what are the consequences to society? How does this affect hospitals? How does this affect your military? How does this affect your water supply? How does this affect your food supply? Things like that. If you can imagine the level of confusion that could occur. All right, I'm just going to hit on a couple things and then we'll answer some questions. We're good. We need folks like you all. We really do need to address this on a large scale. We're right now responding to something that's occurring up at the Secretary of Energy level. Manhattan Project 2 is what it's being called, around AI. What are the big challenges around artificial intelligence? One of them is around energy and energy systems. We need folks that really can understand and help us architect the energy system of the future. And how do we evolve the system of today to what we think it should look like in the future? Given that there are investments in today's energy infrastructure that are going to be there for another 20, 30 years, that we know cannot respond to the threats we're going to be seeing in 5 years. Because I don't know, I couldn't predict what kinds of things we're going to be running into in 5 years. We need folks that really understand software and the cybersecurity aspects. Not just AI, but technologies like quantum sensing, quantum information systems. At some point, this technology or quantum is going to be, computers will be advanced enough where they can break any of the encryption that we have now, RSA encryption. And of course, computing will be at the core of it. So this is why it's really important for me personally to be here, for us as a national laboratory to be here working with CMU. So I think we're all going in the same direction. Would love to hear more about you and your interests in research in this particular space. Would love to find more ways to collaborate, and happy to answer any questions. All right. Thank you.
Thank you, Juan, for that great talk. We have about 10, 15 minutes for questions, and we'll just jump right into it.
Do you have any comments on the DOE funding cuts that just got announced earlier this week that basically gutted most of the energy field in the U.S.?
My comment is yes, there are cuts. Yeah, as a DOE laboratory, you know, our role is to be here to support what the nation needs and where the resources are. So that's about all I can say on this point. Does it affect us? Absolutely. But we are in the process of working with the Department of Energy to pivot and adjust to their priorities. As a national laboratory, we're an extension of the Department of Energy. We're not federal employees, but all of our assets are owned by the Department of Energy. So ultimately, they decide how they get used. Congress decides where things get funded, and then the DOE and the executive branch decide how to execute that. All right, so we're there to support. We're there as a resource for the nation, but we're also here as a resource to industry. So, you know, we do a lot of work with industry and other government agencies, non-government agency or organizations as well. So it's about all I can give you right now. I don't control budgets. We respond to. Yeah, we execute with what's there.
Any other questions? I have a question.
Sure.
So you know, at least personally, I can't speak on behalf of the folks in the room. When I think about energy security, I think about like cyber attacks that are occurring through wires into electronic systems to like shut them down. But you'd mentioned a few times some of the hardware attacks. And I'm wondering if you can give us just a couple of examples of like, if that attack that were to happen, that happened in Northern California in 2013 during the Boston Marathon bombing, what are some of like the safeguards that have been either put into place or have been researched to put into place after that attack to prevent that type of hardware attack?
Yeah, I think overall it's increased the awareness and I think the sensing as a whole. I think the procedures by the utilities on how they respond, they're incorporating, things like even drone technology to more rapidly assess status of systems. So they're taking advantage of technology and where it's evolving to address those things. Those are really challenging. Ultimately, you know, the human threat, even from a cyber perspective, is the most difficult, challenging one. Insider threat is the most, in the cyber world, anybody who works in that particular space knows that is really hard. It is really hard. So tightening down who has access to the systems, how you can more rapidly assess the status and respond to if there is some sort of an event. I would say coupled with that are things that we're still working through, is to understand things like wildfires, right? Which is another essentially physical threat to these systems. Could we more quickly understand when we should disconnect parts of the grid? Are there technologies in there that could protect the system as well? So we're working it from a technology and a procedural perspective as well.
Cool. Okay.
What would be like the top one or two breakthroughs that are on the cusp that you're excited about being released to the public? Hey, yeah, you might be able to comment on.
One or two exciting. I can't talk to anything that isn't already public.
Well, I mean, then you're excited. What are you excited about?
Yeah, I'm super excited about right now this Manhattan Project 2. I think it'll provide hopefully more focus in this AI space. We're having some discussion a little earlier about the fact that AI just kind of snuck up on us, right? It seems like a couple of years ago, ChatGPT all of a sudden was becoming like, what's this new thing? It's only been a couple of years. I can't remember when that really started taking off, right? And we were just talking about ChatGPT. Now we're hearing about things like AI developed publications, research pubs. Have you seen that? Right? And the fact that, how is AI going to affect us? How is it going to affect society? So right now we're trying to figure out what is the government role, because I will tell you, industry is just running with it. Industry is advancing it, incorporating it into anything and everything. So where I see us right now is especially coming from a Manhattan Project laboratory at Sandia, that there's a huge opportunity for us to really help shape for the good, shape the use of AI for the good. The huge challenge on this is that we're not the only country working on this. This is a global thing, and I don't know that we're all on the same page. So there's the what can we do with technology, but there's also the policy aspect that's going to be really important. So I would say I'm excited about working in that space because I think there's just so much uncertainty and unknown.
Thanks for this presentation. I learned a lot more about NREL than I knew before, and I thought I knew a fair amount. So I'm thinking from the perspective of the startup companies that are coming out of CMU and others in our region. There are many potential bits of expertise and resources and so on. Is there a front door for a startup to come through to help get connected to the right places? And do you still have the voucher program to work with startup companies?
We do, and I can connect folks, whoever wants, to our partnerships office. We have a variety of ways to work together in that particular space. There are some partnership programs where we're working with, say, large companies like Wells Fargo and Shell and so on, where they may have hired us essentially to help them evaluate technologies for startups on a spectrum of different technologies. So yes, happy to connect you with our partnerships team.
Hi, this is Woody from Heinz College. Thank you for the great talk. I share the same sentiment that I learned a lot from your talk about the NREL. So on top of that, I wonder, I mean, I would assume a lot of people, a lot of entities, different agencies are working toward the same goal, trying to, develop plans, strategies in response to the same or similar threats. So I wonder what kind of role that NREL is playing in this kind of process. And building on top of that, I also kind of curious what are you expecting from your visit here at the CMU? You know, I guess, as Daniel just mentioned, CMU is a very versatile place in terms of energy-related research. But I guess you probably have your own priority. You're probably looking for something that is more specific during this visit. So just
Okay. So as a laboratory, our role is around the energy system space, with yes, renewable technology at the core of the mission, but that's not the only piece. Again, we work in the generation space and with partners around how you incorporate small modular reactors. We have some work going on. We have our own gas microturbine synchronous generator emulation. So we have a lot of different things that we do at the laboratory beyond renewables. So, but our mission space, when you ask, where's NREL space, we will stay within the energy lane. Like we're not working, on technology for medical applications or entertainment, right? Things like that. So we stay within that space. My personal interest, given we have now an umbrella MOU between NREL and Carnegie Mellon, so which includes materials and cyber and energy, a lot of different things like that. I'm here as the executive responsible for the power grid and the cyber security and national security space. My interest is in exploring partnerships, collaborative research, a lot of different things in that particular area. Student hires, postdocs, different things like that as well. So we're going to explore all of those things, but for me, that's my niche for the laboratory. Okay.
Thank you. Hi, thank you for coming here. I really enjoyed your talk. I was wondering when you brought up like Manhattan Project 2 earlier, like what the connections are, like the main connections are between increasing like nuclear energy production and like using AI for like good reasons, as you were talking about.
Okay. You're talking about like nuclear generation or?
Yeah. Or like, I'm not really sure exactly what Manhattan Project 2 is working on, but I assumed it was like nuclear plants and like energy
Oh, okay,
generation.
got it.
Yeah.
Not specifically. The linkage between, MP2, Manhattan Project 2, and the first Manhattan Project is the fact that we're working on something that is a really big challenge, right? So first Manhattan Project was all about how is the U.S. going to win World War II and get to a bomb before Germany did, right? A very clear problem, a very big problem at that time. What MP2 is all about is we've already identified the challenge is AI. And what we're trying to do is narrow it down into what are the big things we really need to focus on, because we think AI is really going to change the world significantly. But nobody has a good handle on how that's going to do it. We believe there are going to be a set of areas that I know Department of Energy is going to invest in. And one of them likely, we've proposed that we think AI as applied to energy is a big one. AI as applied probably to something around cyber energy, or cyber is another one. They could be coupled. I don't know. So we're still in the process of shaping what the focus areas are, but the general topic, AI, we think is so, it's going to be so big that bringing in 17 national laboratories, which the original Manhattan Project, the labs didn't exist, but it brought the best minds at the time to solve this big problem. So that's the analogy, is it's bringing the best minds within the country, and right now kind of bringing the national labs, whose mission is to solve the biggest, hardest problems here for the country. That's why they're calling it Manhattan Project 2. Okay.
Thank you for your talk. I also learned a lot, and this is not my field, but it was really interesting. My question is similar to, well, on the lines of your question. You talk about a lot about the cybersecurity aspect and how to make the grid more robust to cyber attacks. The relationship with the Manhattan Project, again, like, is it also the interest of the lab to find ways to use that as a form of deterrence, like instead of a defensive way, but more of a, like a better word, attacking way to potential national security threats?
Our role, ultimately, we respond to whoever's sponsoring or funding our work. So we will advance the technology in a way that furthers the benefits for the nation, I guess is what I'll say. You can take anything that's intended for good and turn it on its head. And that's something we'll also need to think about, is because you want to make sure somebody doesn't take something like that against you. So we work in the entire spectrum, but ultimately we're here to support the nation, to make sure that we bring the best minds to solve the hardest problems for our economy, for our national security, right, and ultimately for the benefit of the common good within the country.
Hi. Thank you, Juan, for your talk. I wrote my question down on my phone, so I'm just gonna read it this way. With data centers being built, like scheduled to be built at such a fast pace, I'm actually curious, if there's any like nationwide allocations and plans for the grid to be like on standby power, or do you like build infrastructure like substations for the future, and like does NREL have any part to play in this?
Okay.
Thank you.
So there's multiple pieces in that. So at a high level, in the way the grid operates, there are more than 3,000 utilities in the U.S. Okay. That already tells you how complicated this problem is. And many of those are, I talked about the three major grids, the Eastern Interconnect. Essentially, you cut the country in half, go down to Texas. Texas is its own grid, but then you have the Western and then the Eastern. Within each of those, you have multiple utilities, large transmission investor-owned utilities as well as smaller utilities. And we're hearing even I had a meeting this past week with the American Public Power Association, where they have the small city-owned utilities. And they're having to deal with things at their level where data centers are wanting to come into play. So there isn't really like one big policy that addresses the challenges of data center integration, because they're going to take place all over the country, near small utilities and large utilities, all kinds of different places. So they really have to address the needs for data centers on a local level, because the capabilities that each utility have will be very unique to how they evolved over time. So there may be some common practices for how they do things, but they really have to do things on a local level. Let's see, with regards to NREL's role in this particular space, I mentioned I think in my bio, one of the things I did over the past 7 years was I was the co-chair for something called the Grid Modernization Laboratory Consortium. GMLC was formed in 2015, and that brought together 14 of the DOE labs actually had research capability around the grid. And so my role as a co-chair working with my colleague was to bring the breadth of all those capabilities to address these challenges. So we've done a lot of work over the past 10 years to help the industry, help the utilities move forward. I will tell you what we're seeing as far as needs from data centers, where it's not really in there. So we have to do a lot more in that particular space. There's no single place to solve all this problem, but some of the challenges, I'll say that we are in a good position with the industry, with bringing the labs together, that if we work together, we can address some of these really big problems. And you're right, data centers are coming in very rapidly, and they're coming in on shorter time horizons than we can build new power plants. If there is an interconnection process, if somebody wants to add new generation to the grid somewhere, there's actually a process to be able to add that. That process takes several years. If you want to build a new generation plant as well, right now, it takes about, I think, if you wanted to build a new gas plant, for example, you guys don't have as much gas out here, right? I don't know if the gas is there. If you want to build a new gas plant, you're in the queue. It probably takes you 5 years to get that hardware. So if you didn't order it today, you're not going to see it under this administration. I'll tell you that. It isn't going to be there. So we're trying to find ways to speed things up, because data centers are coming in much more faster than we can build out the generator. So some of the things we're doing as well are things like reconductoring, and so basically increase the throughput of our power grid so they can handle more power. All right, and so that's one way of putting more power on the grid with what you already have, decrease the losses and things like that, right? So hopefully I answered your questions. Okay.
Hi, great talk, thank you. So you touched on this a bit before, but thinking about DERs and opportunity for grid forming inverters to, say, island rooftop solar if there's a power outage, etc. I have 3 questions. The last one I'm most interested in the answer to. So first one, does that ability to either island or be powered by the grid make the computation of load balancing harder? Is that something that makes the problem in that space worse? Do these DERs make any of the cybersecurity issues better or worse because they can connect or not connect? And then finally, are the legal barriers to some of these things like DERs or islanding, are those greater than the technological barriers? And how is NREL engaging with some of those legal or policy issues?
Okay. On the first 2 questions, with regards to the technology, does it make things better or worse? Is that technology going to improve resilience? I guess is ultimately where you want to get to. The real answer is it depends. And you want to make sure this is seamless integration of things like microgrids and virtual power plants, because if those systems disconnect without full coordination with the rest of the grid, it can actually cause instabilities on the bulk grid. If somebody were to go and access and drop just a bunch of the load in an area, that can affect it. So I'll say right now, it's a few years ago when I was working in the microgrid space, the biggest challenge was really just getting the approvals and the procedures in place. From a physics perspective, that we knew how to connect things. From an electrical perspective, we knew how to set up microgrids, and then get to the point though where everybody on both sides of, say, a microgrid was fully synchronized to know, when is it okay to disconnect? When is it okay to reconnect? And how do I do that? And how do I make sure I don't cause problems when I disconnect or reconnect? So that coordination is hugely important. And so we're at a point where we're still evolving that, and the processes and the procedures move relatively slowly, I'll say, because the utility sector is pretty conservative. They don't want the lights to go out. With regards to, the area around policies, and I'll say policies, regulations, standards, and so on, we don't make policy. We inform. We help the standards bodies, and so in the Unify space, we participate in a lot of different standards bodies to provide objective perspective, because anybody who's working standards, I spent some time working some cyber SCADA standards back in the day. Boy, it is really interesting to watch vendors' posture, right? You have different companies that will attend these sessions to try to position their technology to that might be most aligned with, they try to push the standard in a way that's going to benefit them. And so as DOE labs, then we're able to be more objective and say, this is what we think will be the best for the sector, right? So we do play roles like that. We do a lot to inform policymakers. For example, we'll do briefings for folks on the Hill. They have things like National Lab Days where we'll brief Congress about different technologies. I've had the privilege of giving 3 congressional testimonies. So that's where they've asked me to, what's the state of technology? What's the state of this? Could we do a black start with all renewables and solar? Or how is solar going to work with nuclear? So we can inform the state of technology and the state of research, and identify areas that might need more investment, identify where there are gaps, things like that. So yes, we play in all those roles. We do a lot of work around like markets, understanding how markets are going to be affected, or maybe some things they should consider, right? Because the energy market is a whole big complex thing in itself as well. Okay.
You have been amazing questions. I think we have time for one last question.
I see a hand here.
Yeah.
Should have tossed or something. Hi, I was just wondering if you could speak to whether there's been any research on like reliability for data centers if they are feeding critical operations at a utility, like the interdependency between a data center and a utility using like cloud-based services for hazard mitigation. Like, is there any sort of liability concern? Like, you have to use this data center that has this kind of power backup, that has this kind of reliability, or is meeting a reliability standard?
I think we're in the early stages of that kind of research. I can't say that I'm current on reading any publications in that space, but I'll say we are definitely asking those questions, and you'll probably see some work coming out of our lab and probably some other places as well. I don't think it's well understood. So there's an opportunity if you're working in that space.
All right. Well, Juan, thank you so much. We're honored to have you here today. Thank you for this wonderful talk. Thank you for all the wonderful questions, and thank you for being here. Please join me in giving Juan a last round of applause. That's good.